Welcome everyone. Welcome to see you all after 3-4 days. And as you know, before these 3-4 days, we were doing the nuclear and electronics revision, and I gave you some of the DPPs. And today we are going to discuss the doubts of the nuclear physics DPPs. Although not so many doubts came in the group, so there were 5 to 6 doubts, and I will be taking all of them. And after this, I will be also giving you the today's work, and which is a proper lectures which I already uploaded on the YouTube, as well as the course as I mentioned. So let's begin very quickly. So this was the first doubt which was shared by 2 people, and it seems like it's a common doubt. So let's see what is there. So they are saying that what is the energy required? So this is a doubt from nuclear properties DPP, question number 8. Okay. So the question is something like this: the what is the energy required to remove the last neutron from 4 helium? Okay. So you want to remove the neutron. So from the 4 helium, how much energy do you need? First of all, why do I need energy? Why it cannot emit itself? Right. So let's understand. So by the way, all the masses are given to you. So whatever information you need is here. Okay. So perfectly fine. So in the beginning, I have a 4 helium. So 4 helium means helium has a 2 atomic number. So there are 2 protons, and total mass number is 4. So it means there are 2 neutrons, 2 protons, 2 neutrons. Total is 4. Okay. So this is a number of protons. This is a number of neutrons, and this is a total mass number. Okay. If I remove the neutron, for say, so proton still remains 2. Neutrons become 1, right? And the mass number is 3. Okay. Now the mass number is 3, and if I remove it, so I will also have one extra neutron beam. So this is my nuclear reaction, and the question is how much energy I need to do this nuclear reaction. Basically, if I want to do this, how much energy is required, right? So masses are given. For example, the mass of 4 helium, where is the 4 helium? This is a 4 helium. So the mass of 4 helium is 4.0026, which is clearly written here. Then the mass of 3 helium, which is here, is 3.0160. And mass of the 1 neutron, which is here, is basically 1.0087. Now you can clearly see that this is your mass of reactants. Reactants means initial. And this is your mass of the products, final. And if I add them, I will get 4.0247, which basically means that my initial mass is less than the final mass. Okay. So mass of the reactants is less than the mass of the products. So from where this extra mass is coming? So let's say you have someone, and all of a sudden this person increased his mass. From where this mass is coming? Nucleus cannot eat the food to gain his mass. So from where this mass came? This mass came from the energy. Which energy? The energy which I did. So I did the energy. I supplied the energy using the Einstein's relativity theory. The nucleus converted my energy into mass, and the mass of the overall mass increased. That is why I need energy. Okay. If the final mass was less than the initial mass, then the energy would have been released, because where did that extra mass go? That extra mass went into energy. Okay. So two things can happen. If your initial mass is less, final mass is more, it means who will give this extra energy, this extra mass? I will give that. I gave the energy. I gave the energy. Nucleus converted that energy into mass and increased its mass. So all I have to do is find the difference in mass. So what is the difference of mass? So if I do the difference of them, I will get 0.0221 U. U is, is atomic mass unit. And now I can convert this mass into energy, because energy is asked. So that is mc square. So this is m, this is c square. So 0.0221 and then u into c square. So that is given to you. 1 AMU into c square is 931.5 mega electron. So that is why you see I have 931.5 mega electron volt. If I multiply both of them, I will get 20.586 mega electron volt, which is my option number D. Yes, any conceptual or calculation doubt anyone have in this? Yes, please. Is it clear to all? Why this happened? What happens is so this is the mass of the reactants. This is a mass of the product. Okay. Negative means that this thing is bigger, right? And you can see here, if I add this thing is bigger than this, so it means product mass is more than the reactant mass. So you had a reactant, you had a product, the mass increased. Why the mass increased? Right? Because I gave the energy. That energy was converted to mass. That is why mass increased. That is the meaning of it. Okay? That is what is asked here. Energy required to remove. Why energy was required? Why energy required? Because the mass is increasing. And only way the mass can increase is, okay, I gave the energy and the nucleus converted that energy into mass. And the mass of the product became bigger than the mass of the reactor. Okay? So that is the physics. Yes.
Okay, sir. Thanks.
Clear, everyone? Yeah.
Yes, sir.
So next problem 2 and problem 3 are from the rotational model of nucleus. By the way, I have so your next work is also related to this, but let's see this problem first of all. Whenever we have a, so let's read the problem first. So if the first excited state of the nucleus, so this is the first excited state of the nucleus, has the energy equals to 93.3 kilovolt electron volt, and then what is the energy of the third excited rotational state? So basically we are in a rotational energy levels. Okay, let me be very clear. The nucleus can have few kind of energies. Number one, binding energies, basically your overall energy of the nucleus. Okay, so first your nucleus has a basic energy, standard energy, because there are protons, neutrons, they are binding with each other, so many things are there. So your nucleus has some energy which is known as a basic energy. Then we have a vibrational energy, and then we have a rotational. Okay, this vibrational and rotational energy comes because of the distorted shape of the nucleus. For example, I will explain this more in a lecture which I have provided you. As for today, we don't need to go into much detail for now, but if you watch that lecture, you will get a very good idea that nucleus shape is not sphere, it is distorted, and how that distortions give rise to new energy levels. Okay, so that is basically the idea. So number one is we have a nucleus which has a basic energy, and then we have vibrational energy, and then we have rotational energy. These are the extra energy, and these energies are coming because of the vibrations and sort of the angular momentum or the distortion of shape of the nucleus. The nucleus is continuously changing its shape continuously, and how you might get curiosity in that. So that is what your today's lecture is all about. Later on, this curiosity will be satisfied later on, but we have to understand there are two additional kinds of energies. Okay? Vibrational energy I have covered in detail in the lecture which I'm going to give you today, but rotational I'm going to do it now because that is much easier. Okay? That is much easier. Okay. For now, let's forget about nucleus. Let's completely forget about nucleus, and let's see how we handle rotational energy levels. Rotational energy levels in quantum mechanics, or in atomic physics, or in nuclear physics, or in solid state physics. In any of these in which the quantum systems are involved, how do we study rotational energy? So the first theory came from the back rotational mechanics, or let's say very much go to the linear mechanics or kinematics. So we know kinetic energy is given by half mv square, but this is a translational kinetic energy, which means when you are having a straight line motion. Okay, but when you are rotating, then you have a rotational kinetic energy. So half is half, mass becomes inertia, and v becomes, so linear speed becomes rotating speed, rotational speed, omega. Okay, so that is what we have. So this is the kinetic energy I am interested in. This is my rotational energy. This is a rotational energy. Okay. Okay. Another thing what I can do is I can use another idea which says that angular momentum is equals to I omega. I omega. So I will use my omega as L by I. So I will put it there. So I will get 1 by 2I into L square. Okay. And in quantum mechanics, L square is L into L plus 1 into H cut ka square. And that is the basic idea behind the quantum mechanics. So either you are in quantum mechanics, atomic physics, nuclear physics, solid state physics, in all of these cases, L square is written as small l, which is a quantum number, into L plus 1 into H cut square. Hence, my final energy becomes H cut square by 2I into L plus 1. Okay? So that is my rotational energy levels. This is not just for nucleus. This is for nuclear, atomic, quantum, any sort of rotational energy levels you are dealing with, where L is a quantum number, angular quantum number, or you can even write it in terms of J in nuclear physics. Okay? In nuclear physics, you can even write it in terms of J. You know, you have calculated J using the shell model, right? So you use the shell model and you used to find J, right? So you can convert your L into J in nuclear physics, not in atomic. In atomic, you know, J is a total angular momentum. So there J has a different meaning. Here J has a different. In nuclear physics, you can convert your L into J without any problem. Okay. Okay, I understand that. So this is my going to be my rotational energy. In general, J is going to be 0, 1, 2, 3 in general. But in nuclear physics, J can only take the values 0, 2, 4, 6, 8, and so on. Why? Because in nuclear, one thing we have to satisfy is a mirror symmetry, which comes under when you study particle physics in detail. And even in H.C. Verma sir's lecture, they have not discussed this in too much detail. I tried to look for it. But the idea behind that, which I obtained from H.C. Verma sir's lecture, is that it is because of the mirror symmetry. Your nucleus can distort, but it always have to maintain the mirror symmetry while distorting. So when the nucleus is distorting, the mirror symmetry always have to be maintained. Okay? That is, in order to satisfy that condition, J cannot take the value 1, 3, 5, and 7. We don't need much more detail about that. But in nuclear physics, J can only take the value 0, 2, 4, 6, 8, and so on. Okay. Now, let's come back to our question, which is saying that for the first excited state, okay, what is going to be my first excited state? So this is going to be my ground state. So this is going to be my first excited state. So let's put J2. So if I put J2, I get 2 into 3, which is 6. H cut square by 2I is as such. And the energy is given to me as 19.3, 93.3. Okay? I just put the value. Okay. That is given, that was given to me. Now what is asked from me? They are asking what is the energy of the third excited state. So I need the energy of third excited state. Okay? So if I want the energy for the third excited state, what is going to be my J? So ground state, first excited state, second excited state, and third excited state. It means for the third excited state, J is 6. So now I put J6. So I get H cut square by 2I into 6 into 7. And this is the energy I need to find. So all I do is just divide. So if I divide, I will get E by 93.3 and then 42 by 6, which is nothing but 7. And then I can just multiply 93.3 here. So I will get 653.1 kilo electron, which is going to be my option number B. Okay. So first thing first, what are the rotational energy levels? These are my rotational energy levels. Why they come? Because of the distortion of the nucleus and continuously changing shape of the nucleus. In nuclear physics, J can take the value 0, 2, 4, 6, 8, so on. Why? Because the mirror symmetry has to be obtained. And that's all. That is, then I just need to do the mathematics. Any doubt in this model, rotational model of nucleus? Yes. So then we go for the third question, which is nuclear models. And question number 3. Then what is the problem? So the problem is, this is one of the most difficult problems, and yeah, you will this was little confusing. Okay, so let's see. So they are saying that a single particle energy difference between d orbitals d5 by 2 and d3 by 2 of this nucleus is 5 mega electron. So first of all, he is talking about the d orbital, and he is saying the energy difference between d5 by 2 and d3 by 2 is 5 mega electron. Then what is the energy difference in case of f orbitals? So f orbital will also have the two situations, and that most probably will be 5 by 2 and 7. Let me check. Yeah. So what is the energy difference between these two? Okay. Okay. Perfect. So the energy difference between these two is given, and the energy difference between these two is asked, and the nucleus is given. Nucleus is 114 into 20. In not into 20 means 50. Okay. 50 is the atomic number. If you look at it carefully, very carefully, there are 50 protons and there are 64 neutrons. So this is an even nucleus. So we are not going to use shell model, because according to shell model, even nucleus has no spin, no magnetic moment, and so on. So we are here not interested about the basic energy levels. We are interested about on top of it what we have. Although it should have been mentioned here, but we are here talking about is again rotational energy. Although it is not directly mentioned, but according to our syllabus, the hint is that only thing that you can calculate above this is the rotational energy. Okay? In vibrational energy level, you do not have a proper mechanism to find exact energy levels. You can find the symbols, but what is the energies, that is difficult to calculate. It does not mean that you cannot compare or you cannot do anything. Once you will watch the lecture on vibrational also, you will get better idea. But one thing is very clear, is this is an even nucleus. So we are not talking about the basic energies, because shell model does not talk about even. So what we are talking about here is a addition to shell model. Additional to shell model is a rotational energy levels and then vibration. So we are concerned about the rotation level, more or less. However, it is not directly written, but that was something to hint about. Okay. Okay. So we have two things. One is d 5 by 2 and one is d 3 by 2. Okay. Since it is d orbital, so L is 2. Again, L is 2. It does not change. J is 5 by 2, and in this case, J is 3 by 2. Okay. If I call this thing as capital J, then this is going to be J plus 1. Why I am calling this J? Just for simply you can say simplify my things. Let's call this as capital J, and if this is capital J, then this is going to be J plus 1. Okay. And I need the energy difference between them. So let's do the energy difference. First of all, you know what is the energies. So energies is h cut square by 2i j into j plus 1, and now I need the energy difference between them. So if I do the energy difference between them, h cut square by 2i will be common. Okay. And then first I take it j plus, means I put j as j plus 1, small j as capital J plus 1. So that will become, here I will have is j plus 1, and here I will have is a j plus 2, minus, then I put my j as this, right? J as this, so I get j into j plus 1. Now capital J plus 1 can be taken common, and then j plus 1 minus j will cancel, and you will be left with this, sorry, j plus 2 minus j, and you will be left with this a 2, and that 2 you see here. Okay. It means the energy difference is given by h cut square by 2i into 2 into capital J plus 1. Now the question is, what is capital J? What is this capital J? Capital J is 3 by 2. We know. We have put this thing as 3 by 2. So capital J is 3 by 2. So this thing becomes 5 by 2. So this is your energy difference. And it is given to you. In the first case, it is given to you. It is 5 megaelectron. So it is 5 megaelectron. Okay. Now I need an energy difference between f orbitals. So if D is going from 5 by 2, 3 by 2 to 5 by 2, F will go from 5 by 2 to 7 by 2. Okay, because L is increased by 1, right? So increased by 1, right? How do you get J? First of all, how do you get J? You get a J by adding L and S, right? And S for a neutron or a proton is half, and L is for a d orbital is 2. So if you do 2 minus half, you get 3 by 2, and if you do 2 plus half, you get 5 by 2. That is why you have these two energy levels. But if I'm talking about f orbital, for f orbital, L is 3, and this S for a neutron or a proton is still half. Now if you add, you will get 7 by 2 or you will get 5 by 2. Now I need is energy difference between 5 by 2 and 7 by 2. Initially, I calculated the energy difference between 3 by 2 and 5 by 2, which was given to me. Energy difference between 3 by 2 and 5 by 2 was given to me. And I used my rotational energy formula, and I said, okay, this is this. This is this I equation I get. Now I need the relation between 5 by 2 and 7 by 2. 5 by 2, 7 by 2. Okay, so now I will put 5 by 2 here. Initially, I put 3 by 2 here. Now I will put 5 by 2 here. So then it will become 7 by 2. Okay? And this is something I need to find. In the first case, it was given. It was 5. But now I don't know. I need to find this. So one equation I get is this second, and one I already got is first. Now I divide them. If I do, I will get delta E by 5. And then 7 by 2 divided by 5 by 2, which is going to be 2 cancel, 5 also cancel. So only thing you left is 7 mega electron volt. So that is why your answer to this question is 7 mega electron volt, which is option number C. So first hint, even nucleus. So shell model is out of the game. So we will use rotational energy levels. Rotational energy levels. So the energy difference between 3 by 2 level and 5 by 2 level is given. You know what is the energy formula for rotational this. I can find that difference between 3 by 2 and 5 by 2. First you put J as 3 by 2, then you put J as 5 by 2, and you calculate the difference. Okay. Then they are asking what is the energy difference between the f orbitals. For f orbitals, the energy levels are going to be 5 by 2 and 7 by 2. And then you also do the same maths. You get two equations, you just take the ratio of them, and then you get the final answer. Okay. Yes, this was a tricky question. Any doubt you have in this problem, please go ahead. Then the question number 4, which is from nuclear properties, and this is going to be question 15. Although this was not a doubt as such, the calculation mistake was there on the part of the student who asked this. So let me clear that calculation mistake. So this kind of problems we did in the binding energy, especially liquid drop model. So for a semi-empirical mass formula, binding energy is given to you. So binding energy is given, and all the values of constants are also given. And they are asking what is the value of Z for the most stable nucleus. Value of Z is asked, and A is fixed. So we need to minimize binding energy with respect to Z. So you know we do dB by dZ. So if you do dB by dZ, you will get this equation. Okay. And then I have very systematically did all the steps by myself, and then I realized the answer which is coming is 19.68, which is 20, which is closer to 20. And since the integer was asked, that is why the answer should be 20. And the student who asked this question said that answer should be 19.4. No, you have a calculation mistake here. I did the calculation by myself, and you can see the steps. The systematic calculation lead us to the answer 19.7, which is roughly 20. Okay. So there is nothing more in this question. Yeah, is it clear? Yes. Yeah, I hope so. So you can see my steps later on. I will share this PDF with you, and you will see that any mistake you might have made in the calculation. Okay. Chaliye. Now question number 5. The lecture which I will be giving you today, this question will be done on the basis of that. Exact question has been discussed in the lecture, so I don't need to cover it right now. So I am going to quote the lecture after this video. Okay. Okay. And then comes the last problem. Yeah, this is never been asked in CSIR net, but I felt okay, maybe this could be asked. So there is only one formula that will be useful for this, and the proof of this formula is given in Crane book. So what is the question is that according to the shell model, we need to use the shell model for this nucleus, and we need to find electrical quadrupole moment. Okay. So electrical quadrupole moment is something which tells us if the shape of the nucleus is spherical or not. If the shape of the nucleus is spherical, then the quadrupole moment will be 0. But if it is not spherical, then it is not 0. Okay. So ideally we assume that the nucleus is a sphere, but in reality it is not. The average of it is not sphere. It might be little bit deviated, just like Earth. So that will be calculated using the quadrupole moment. So quadrupole moment formula according to shell model is this. Okay. And minus 3 by 5, 2j minus 1 by 2j plus 2. I never gave you this formula before, so that is why I'm mentioning you now, into r square. If I get 90 in some answer, then we take it is, I also get this only, but I was asking if I get 19.4 in some answer, then yes, then you take 19. Because you see, so basically if this peak is at 19.4, then the closest nucleus to this peak is 19. Okay, so we need to see that who is the closest nucleus to this peak, because the 20 wala will be little bit far. Okay, 19 or 20 both are not at the peak, but we need to see who is closer to the peak. So the general rounding of will be applied. Okay. Yeah, perfect. And then this is a formula for a quadrupole movement, and yes, r is a radius, so you know how to find radius. Radius is calculated using r naught into a ki power 1 by 3. And how to find j? J is using the shell model. You use the shell model and find the spin, right? So just do the same thing and find the j. Okay, so then put the values, you will get the answer. So this formula you can keep in mind while finding the quadrupole movement. You can note it down in your notebook, and before going to the exam you can have this revised. Okay, so these were the questions which were asked in the group before the lecture and which I have covered now. Now I will not take much of your time and will give you to this homework, which is going to be this. So 2 lectures are uploaded on YouTube and as well as in the course of free capsule physics course. So the playlist you see in the YouTube, I'm maintaining the playlist. So you can see that the one lecture is on the form factor. Form factor. So watch the form factor lecture. This lecture is important for JAM, GATE and NET. Even the JAM, it is important. Okay. Then the second lecture is on vibrational energy levels. Vibrational energy levels. This lecture is only important for GATE and NET. Okay. No additional DPP is required for them because the question of these are already in your DPPs. As you see, today you ask the doubts of that as well. So these 2 lectures you can do today, and then we will go for the next lectures tomorrow. I will let you know all the information in the group about the tomorrow's schedule and everything. Okay. So that is all from my side. Any doubt you want to ask from today's